Okay, hello everyone. Um, it is 2025, and what I want to show you here is how far we've gotten with this tool, PowerXRD. We now are offering Rietveld Refinement, a very early and nascent and not too naive Rietveld Refinement module for our tool, right? If you go to the wiki site here, you'll see that now it's a little bit more updated. It's even like a little bit more lean and everything. We have the wiki has this page on Rietveld Refinement and PowerXRD. It gives you a little bit more details of what we've done, what is implemented here now. We have Rietveld Refinement now, but it's just we just have it for the cubic pattern. Of course, it's in the future plans to expand beyond cubic crystal structures. Just maybe we could do orthorhombic and others, but I don't really have don't spend too much time with this. I would love to have some open source collaborators. Otherwise, you just have to wait until like I add those patterns or structures. Sorry, those theoretical structures myself. But nonetheless, I think that we do have something already like decent for the time being with the CubicModel analysis. And here are some examples that you can actually copy paste and you can work them and they will be fine, right? You can also go to PowerXRD and to the repo. There's a redo docs and there's a Rietveld Refinement section now that also has copy pastable information here that you can paste and try yourself. But we're not gonna do that. We're actually gonna go and show you the bones. So PowerXRD Rietveld Refinement modules. So this is what this video is about. What you're gonna do is you can clone this repository in your computer. Okay. We're gonna go git clone and that. I actually have already cloned it, so I don't have to do that. Okay, so I'm just gonna access it. After you've cloned it, just like change the directory to your clone repo. And what you're gonna do is now you can open it with Visual Studio Code. Okay. Now the tutorial told you if you went to the Rietveld Refinement, it told you that you can start with hello Rietveld.py. Okay. And there are actually hello Rietveld.py scripts on the directory of the GitHub project on the repo, right? If you've cloned it, you can actually ls the full project, and you'll see that we have some files there, hello Rietveld long and hello Rietveld workflow, which are here. I've opened the repository here with Visual Studio Code. And this is actually what you see, right? You see the hello Rietveld workflow and hello Rietveld long. We'll start with hello Rietveld workflow, okay? And for hello Rietveld, sorry, it's mouthful, Rietveld workflow, well, we're gonna use a workflow, the refinement workflow class to simplify, to streamline the full analysis. You can see that we're gonna need to import. We need to import the PowerXRD package, this refine meth module from PowerXRD, right? We're importing it as RR, okay? And then we're also gonna import the CubicModel class, which is currently the only one we have for Rietveld Refinement. But like I said, I want to expand beyond the CubicModel, okay? And here are just some default refinable parameters that I have for the CubicModel. It doesn't have to be that one because we have several different crystals that have the cubic structure, right? This is just actually I think I need to update this. I think it's perovskite that I've changed it to now, but not I digress. Okay, we're gonna use the CubicModel, and now what we're gonna do after that is we're also gonna load. After we instantiate the CubicModel, we need to take our data and load it, right? So here I'm just gonna use a sample, a completely artificially generated XRD file that has no meaning whatsoever. Okay. It doesn't really pertain to any structure. I made it randomly with some patterns a long time ago. Some mathematics. Okay, it's this one, right? It goes from C6 to 80, and it's an XY file. And we have this refine tool that you can use to load it. We can also then subtract the background with another method from the chart class of PowerXRD. It's very simple. Just input your X and Y, and use the dot backsub method, and it will return the background subtracted variables X and Y, right? After that, we're gonna start with an initial guess for the model parameters. For crystal, let's say that it's, I don't know, I think salt, right? It has this lattice constants. I'm not so sure if it's salt. It's just I think these are also arbitrary. Okay. But what we're gonna do is we're gonna start with an initial guess like we always do on regular Rietveld refinement. And then after our initial guess, we're gonna instantiate this refinement workflow class. What we need as inputs is the CubicModel with those initial parameters as guesses. Right? It's all kind of encapsulated within the model instance that we've instantiated with CubicModel. And we also, the other two inputs are the X and Y from the XRD pattern. Okay. And that full thing is going to be the workflow instance. So RW is our refinement workflow instance now. And with that instance, we're going to call the refine method, right? Now that we have our model, our full model, we're going to refine it by just fitting the scale parameter, just this one, okay, while keeping the other constant. That's basically what this does. And then we're going to plot it with the plot fit method from the workflow class. Okay. We're going to make this a little bigger. And what you're going to need to do is you're going to need to create a virtual environment with virtual VM. Okay, then just enter. I've already done that, so I just need to access it. Source, VMV, then activate. And now you can pip install your package there, pip install PowerXRD on your virtual environment. Okay. And after that, after you've done that, now what we're going to do is, we're going to run hello Rietveld workflow, which is this Python script. Okay. So we're going to type Python hello Rietveld workflow. Okay. And as you can see, the first plot that we get here and the output that we get from the terminal is it's coming from lines 20 and 21, where line 20, it gives you the refined values, right? The initial value for scale, which was 1000, and then refined it refines all the way from 1000 to 160, close to 163. And you can see that the other parameters were kept constant. Okay. So yeah, that's the first, basically the first pass of regular refinement. After we close the plot, the program is gonna go through the second pass, and in this second pass, we're gonna refine the lattice constant and the Cagliari parameters while holding the others constant, right? Which is kind of like what you do on Rietveld refinement, don't you? Right? Okay, so we close it, and now this one refines. This second pass does that, just what I know. Lines 23 and 24 refines those parameters. And now we have an error here, runtime warning. We may need to correct. There's some things that we still need to patch up on the program on this project. But yeah, nonetheless, you do see that those parameters have been changed slightly, but they've changed. The lattice constant is going from 6 to 6.02 or 0.3. And the Cagliari parameters as well, they've changed substantially, I think. and the other ones were held constant, right? On the previous pass, we had actually changed scale from 100 to 162.97. That in the second pass, it's fixed itself, and you can see that it hasn't changed, right? And everything else has also been fixed. So you can see that now you got like a different manifestation, different pattern from the refined fit, that it may get a little closer to the experimental, but then again, like I told you, the experimental was actually it's PowerXRD data does not really mean anything, right? I just made it with some random mathematics here, but nonetheless, that's what you get. After we close it, we have also a save log method from the workflow class, and this save log method, what it does is it gives you a JSON file, which shows you all the states that have been changed on the full set that has been changed in every pass for the Rietveld refinement parameters, right? So I could calc here my Rietveld status. You can see that at first, right, we just fit it for the scale, right? Scale goes from 1000 to 163. And then on the second pass, we fit it for the first three parameters, right? The lattice constant and the Cagliari parameters here. So it's always great. And that file is actually here, it's created, right? In the same place where you execute your script, okay? That's here. You can add more passes if you'd like, right? But that's basically how you can use the workflow to make your to help you with your XRT analysis in a different way. Okay. Now we're gonna try this hello Rietveld long routine as well. Hello Rietveld long is a little different because in hello Rietveld long you do not instantiate the refinement workflow class like you do in this other script, right? So, but all in all, it can give you a feel of more control because it's a little bit more low level manipulation here. So we also import some modules here. We import the refine module and the CubicModel class from PowerXRD model. Like I said, we only have CubicModel right now. And the first step would be to load the pattern. If we don't provide the method with any file name, what it does is it will create an artificial experimental pattern from the CubicModel itself. So if you click here on the method, right, the method by default, it does that. If there's no path, it will just take the CubicModel, the current guessed lattice parameters from the CubicModel, the default ones, which are this, right? And what it does is then it will take it and it will make the pattern based on it, and just introduce some noise, right, with a random function. Okay, that's actually what we want to do for this example. I think it all hits a little bit closer to home because what we're gonna do is we already have a decent idea of what the lattice parameters will be, right? The theoretical ones are these ones, right? But maybe we have an idea that they are closer to these values, okay? So that's basically what's happening. We loaded that. By loading that data, we just create synthetic data based on the CubicModel, right? And now we also, like I said, we define these. These are our guesses of the initial parameters. We print them here. And in the first pass, we're just gonna also refine only the scale, okay? So what we do is, I'm actually gonna put them side by side here. I think that would be fun and good. I've never used Copilot. I don't think I ever will. Whoops, what did I do? Okay, sorry. Let me open it again. Okay, sorry. Okay, so this is the hello Rietveld long file, like I told you before, right? as I've told you before. Now, the first pass, like I said, it will do, it will run this refine method. And now it's a little different than the workflow script, right? Because in the workflow script, we were actually using the refine method, a refine method from the refiner workflow class. And that one just takes the list of parameters. But in hello rival wrong, this is not the methods from that class. This is actually a function from the refine module. And that function requires or needs the model that we use, which is the CubicModel, right? Which also it incorporates or integrates the parameters that are currently there. Okay. And the refine, what it does is it modifies the parameters in place, right? So you don't need to like define model equal r refine, right? Okay. And then it also takes the XRD pattern data. You need to put it here, X and Y experimental. Then that's where you define the variable or the parameter that you want to fit while keeping the other constants. And then we have this option to save all the parameters as well. We can save it in any list. We just instantiated the list here in line 8, so that's going to save it there. And that's basically what we do here, right? It's a little bit more extensive, but it helps, and I'll show you where it does actually help, right? So we'll run Python hello right belong, and you can see that that's the first problem we see here. We are just fitting for the lattice constant, right? And right on the dot, we already start with a good not quite a match, but it's converging the theoretical pattern to the experimental already. However, we do see that the background, it is completely off, right? It's shifted downwards. And that makes a lot of sense because our initial guesses for background slope and intercept were 0. So it's starting there, and it's because it's fixed. And that's not what we're changing, is that's what we get. We are just like refining here for the scale. And so that's a good segue to do the second pass, and where we refine the background. Here we do allow the background parameters to change while keeping the other constant, right? And we are also saving the parameters, and that's what we're gonna do in the next shot after I close the speaker. Okay, and now you can see that the background has shifted upwards, right? And it's giving us a little bit more of an accurate match between experimental and theoretical. Okay. Now, we can see also the history here, right? Current model parameters and everything, right? That they have been changed. In principle, we are actually saving everything here also under save stages, but I'm not like going to display it in the end, though we could, right? So that's the second pass. Now, the third pass, we're just going to change the lattice constant. We're going to fit it while keeping the other constant and saying constant too many times. Okay, but yeah, you get the drift, right? We are just input the same parameters here, and we modify. We're refining for that one, and then line 32 will just plot the progression of that, and you can get like you see some peaks are already matching with some others from the experimental, right? Now, what we can do, what's interesting is that we can also set up an initial guess to some of the parameters before we do the refinement, which is what we are gonna do on the fourth pass here. We're also gonna fit for the refine for the lattice constant again while keeping the other constant, but we are gonna give it a different guess here instead of like just like it was before, right? Because before it gave us a refined value of 3.99999, we're actually gonna give it a guess that may come closer, which is 3.93. Okay. And what's great about this is that we can do this in place, right? Just keep in mind that, like I said, everything, the model is actually being mutated by the refine method, by the refine function in place. So when we run that, it actually does internal changes to model. So if we define the parameters before the refinement, then it will change it. And then when we do the refinement, it can produce more changes to it. And, and basically, generate a new model, not a new model instance, but change the constructor variable, right? After that method has run, okay? And then we can also save it as stages. So that's what's going to happen in pass number 4 here. Okay, and now you can see that it's perfect, basically. Everything is aligning, right? We're already close. We can say now that, yeah, this is closer, very close to our experimental, right? If you get closer, I mean, there is a little bit of a change here on the background that we may need to change, right? You can also see that if we go further on pass number 5, then it's giving us nonsense, right? Perhaps it's that it's found, I'm not so sure what's happening here. Maybe it happens in common Rietveld analysis. But maybe what's happening is that we are, because the results were already really good, it's like doing some exploration on its own, and maybe it's diverting too much from what should be the most accurate tier. Well, my most accurate match. But then again, you know, I may need to do some. If you do understand what's happening here, I would really appreciate it in the comments. But nonetheless, you know, like I said, this is a package that is still in its very nascent stages. I would like benefit greatly if we could have like collaborators, people to open in discussion with this, maybe like develop the package or use it for their work, right? But yeah, that's what's happening here. You can see that after pass 5, it already like kind of like it just destroyed itself, right? The fit. So, and on the 6th one, don't even mention it, right? So what we can do here is, I guess, we can just comment out these ones, and we can try to refine the background right after pass 4, right? Because I think that I told you, yeah, there was something here that the background was still a little off here from the refinement of pass number 4. So maybe we can do a pass 5B here. Okay, where we just refine the background, slope and intercept. And yeah, let's actually print the safe stages after that, okay? The list of all the safe stages. I'm gonna comment out these plots because we've already seen them happen, go in action, right? And I'm just gonna not comment out pass number 4, so we'll go all the way there, okay? Now, if we comment out these plots, just gonna go through all of those passes until hitting pass 4, and then we'll plot it, right? So you can see it's gone all the way to pass number 4, where we were really close, right? I think that we were here, we had a very close match and just not so much for the background. But on this optional pass 5, we are refining for the background again. Let's see what it does. And yeah, it doesn't change much, unfortunately, right? But yeah, so and yeah, so anyways, and the last print that I have here is just printing all the safe stages, which is what I've done. What we have in this big chunk of code, right? So that's all that we have right now for the Rietveld refinement features of PowerXRD. I hope that you found this video useful, or at the very least interesting or compelling to watch, fun to watch, right? If you also think that you can benefit from making some changes in the development yourself, yeah, don't hesitate to send me messages on the issues, under the issues of this package, as a PowerXRD, even with suggestions. And if you'd like to even like make changes to the code base, I'd be more than happy to have you contribute to the package. All right. Up until then, I'll see you on the next one. Thanks.